And also thank you everyone for being here. It's quite a group, and thanks so much for being here. And yeah, today I would like to talk about my PhD work, evaluating and designing computing systems for the future of work. So I'd like to start this talk by posing a question on everyone. What computing technology would improve human collaboration and decision-making? Well, someone from 120 years ago started to think about this particular question. English writer Arthur Mee wrote the following back in 1898. If, as it is said to be not unlikely in the near future, the principle of sight is applied to the telephone as well as that of sound, Earth will be in truth a paradise, and distance will lose its enchantment by being abolished altogether. As you might have guessed out, he was talking about something that is similar to what we have known as video conferencing today. And indeed, 120 years later, we now indeed have this kind of video conference technologies. We have Zoom, Microsoft Teams, and we also have messaging apps like Slack to help us even getting closer at workplace. We also have sophisticated computing devices like AR and VR, which give us a different experience at the workplace. And more recently, have this wave of AI, from ChatGPT, GitHub Copilot to Microsoft Copilot, which drastically changed our way we get things done at work, improve our productivity, and sometimes even our creativity. So the question really becomes, given all the advances in technologies these days, have we already developed the ideal workplace technologies? Are we living in a paradise as suggested by Arthur Mee 120 years ago? Well, the landscape is really vague and unclear. There have been mixed views on current workplace technologies. On one hand, there have been positive sentiments. For example, in this New York Times article, someone is saying distance matters much less now. Because of the technology these days, we are actually inching closer and closer to replicating the office. And we have articles like this with title, "Why is Zoom suddenly everywhere? It's easy and fun to use." On the other side, also about Zoom, and another article in the New York Times has the title like this, "Why Zoom is Terrible." And I would say, debates on the usefulness of computing technologies, they're not unique to workplace scenario. They also apply to other scenarios as well, such as education, relationship, and health, where we have seen lots of discussions and debates on whether certain technologies has been helping or hurting that particular scenario. So the thing that I've become really interested in is that rather than arguing back and forth with each other on whether technology is helping or hurting, how do we navigate such disagreements and make progress on computing technologies? I would argue it's perhaps time to study computing technologies as a science of the artificial. And this particular term is proposed by Simon, who is a pioneer in artificial intelligence and in many other fields, such as decision-making theory. And this particular book, which is written back in 1969, is themed around how artificial phenomena ought to be categorized. And Simon discussed whether such phenomena belong within the domain of science in a similar way as natural subjects such as physics. Specifically, Simon wrote the following: "Natural science is knowledge about natural objects and phenomena. We asked whether there cannot also be artificial science knowledge about artificial objects and phenomena." And in this book, Simon gave the high-level vision about some important factors that would contribute towards the science of the artificial. So there are empirical evidence, technical methods, and design. And specifically, Simon wrote the following about the empirical evidence. The contingency of artificial phenomena has always created doubts as to whether they fall properly within the context of science. The general problem is to show how empirical propositions can be made at all about systems. And in terms of technical methods, throughout the book, Simon emphasized the importance of modeling, simulation, as well as other technical approach. And finally, in terms of design, Simon wrote, it's important to study not only how things are, but also how things ought to be. and my PhD research has been largely influenced by Simon's vision. And I've been following this particular idea and try to make it more concrete with specific technologies and applications. And during my PhD, I've been fascinated by a number of questions. On the empirical evidence side, I'm interested in things like how can we leverage increasingly available large-scale data to study machine behavior and human behavior over computing platforms. In terms of technical methods, I've been interested in asking and answering things like how can we better model, sense, and predict machine behavior and human behavior. And finally, in terms of design, I'm interested in things like how can we design applications that align with our needs and values with powerful computing technologies. And with that vision in mind, during my PhD, I've conducted a number of cross-disciplinary collaborations. I have worked with researchers from human-computer interaction, natural language processing, as well as scholars from management science and sociology. And beyond academia, I get the fortune to work with a number of big tech companies, startups, and nonprofit organizations. While I have diverse interests in many different applications, my core contributions during my PhD has been on this very notion of workplace technologies. And I feel very fortunate during my PhD, I've been contributing a number of works with these 3 dimensions on empirical evidence, technical methods, and design, and published a number of papers in different venues, ranging from HCI to social science. And today, I'd really like to focus on my work during my PhD on workplace technologies, on how I have been leveraging this kind of Simon's vision to study workplace technologies. And specifically, I'd like to give the overview of 3 projects that I did. On the empirical evidence side, I'd like to talk about my work where I've been mining millions of online meetings, emails, and file edits, trying to make sense of people's remote meeting experience during remote work. And in terms of technical methods, I'd like to talk about my work using AI to help us better understand team collaboration. And specifically, in this particular work, I've been thinking about how we can leverage AI, data, and natural language processing, try to classify and even predict ahead of time the team outcome, and in this particular case, team viability. And finally, in terms of design, I'd like to talk about our recent work on how we have been using generative AI and specific large language model to re-envision the way researchers get things done and get feedback. And in this work, I'd like to talk about how we have been using large language model to design a tool to build scientific feedback tool for researchers and the evaluation results through large-scale empirical evidence. And with that, I'd like to dive into specific projects. So the very first project is on large-scale analysis of multitasking behavior during remote meetings, which I get the fortune to collaborate with a number of Microsoft researchers. So the central theme that we are interested here in this particular work is on this notion and this experience that we have a lot during the pandemic period, where we have been talking about things like Zoom fatigue, meeting engagement, and productivity a lot those days. And those discussions have been both over academic publications as well as over public outlets. And in this particular work, our goal is to achieve a systematic understanding of remote meeting multitasking behavior. Why remote meeting? I don't think I need to spend much time here because we have experienced that. Remote work, it has become an essential mode of work ever since the pandemic. And central to remote work are remote meetings through video conferencing tools, which help team members stay connected, collaborate, and function as an organization despite physical distance. And multitasking behavior is some behavior social scientists have studied for a long time, which refers to performing more than one task in parallel or in rapid succession. And prior work has shown multitasking is closely linked to one's productivity and well-being. And multitasking behavior, as we have experienced, is an important meeting experience. And many of us have that particular multitasking behavior during remote meetings, where we have been checking emails or getting other things done during the meetings. Despite its ubiquity, there is a lack of an understanding when, how, and why people engage in multitasking behavior under remote meetings. And beyond that, on the other side, while multitasking is a concept that people have explored for a long time in social science, many of the studies on multitasking over computing platforms, they are relatively limited in coverage, where people have been studying like 20-ish or 30-ish people and to get some kind of conclusions over that kind of observational study. So the other contribution that we want to achieve here is, can we get a large-scale analysis and a better understanding of multitasking behavior and during remote meetings? And we want to achieve that through some sort of mixed methods design. So here are a number of research questions we seek to address here. First of all, how much multitasking is happening during remote meetings? Secondly, what factors associated with multitasking during remote meetings? And thirdly, what do people do when multitasking during remote meetings? And finally, what are the consequences of multitasking during remote meetings? And as I mentioned, in this particular work, we adopt the mixed methods approach. There are two core parts of this study. First of all, there's a large-scale data analysis and regression analysis, where we have been using passively collected data to measure and to reflect objective patterns at scale. And on the other side, to complement this particular telemetry data analysis, we also run a diary study to provide qualitative evidence with the goal to capturing the nuanced experiences and motivations behind multitasking behavior. Let's talk about the telemetry data first. So in this particular study, we collected meeting-related actions from Microsoft Teams, email usage data from Microsoft Outlook, file edits data from SharePoint and OneDrive, and we collected 4 separate week-long snapshots of the data during and before the pandemic of all Microsoft US employees. And with this rich data set, we first derived a number of meeting characteristics, including meeting duration, meeting size, meeting types, hour of the day, day of the week, as the characteristics to represent the particular meetings. And after we've derived those features, we joined the 3 different data sources by unique user identifier, which in this case is the anonymized Microsoft user account. And for each meeting user pair, we label it as email multitasking if the user was found to have at least 1 active email action during the meeting. Otherwise, we assign a non-multitasking label. And similarly, we labeled file multitasking. And after that, we run a conditional logistic regression to understand the relationships between multitasking and meeting characteristics. And the second method that we used here is diary study, so as to complement that quantitative evidence. We have this particular survey question: what have you noticed about multitasking in your recent online meetings, with a list of subprompts? And we run this diary study between mid-April and mid-August 2020, which is around a similar time period where we collect the telemetry data. And in total, we've collected 819 responses. So here are the results that we get from this analysis. First of all, we found from February to May, around 30% of the meetings involve email multitasking, and around 25% of meetings involve file multitasking. And we found that more multitasking may be a possible result of work rhythm adaptation, and that ease of turning on video and audio may encourage more multitasking. And the second conclusion that we get is perhaps the most interesting part of the study, where we have been looking at a number of intrinsic meeting characteristics that are associated with meeting multitasking. We find more multitasking happening in large, long, morning, and recurring meetings, as well as meetings with lower relevance or engagement. And to dive in a little bit here, we find that people are more likely to multitask in larger meetings, where the odds of email multitasking in meetings with over 10 attendees are 2.16 times the odds of meetings with 2 attendees. People are more likely to multitask in longer meetings, where the odds of email multitasking in meetings over 80 minutes are 6.21 times the odds of 0 to 20-minute meetings. These 2 findings are intuitive and align with our experience. I think what is really cool about this data set is that we can also uncover some patterns that are not that obvious. For example, we find here people are more likely to multitask in morning meetings. That the odds of email multitasking in morning meetings are 1.86 times the odds of after-hour baseline, and it's also higher than afternoon meetings. And we get some kind of qualitative evidence from the diary study. And this particular participant is saying, I will try to glimpse at email more if a meeting is the first thing I do for work in the morning. So that's schedule related. We also hear from people that people are more likely to multitask in recurring meetings. Through the telemetry data analysis, we find that the odds of email multitasking in recurring meetings are 1.59 times the odds of one-off or ad hoc meetings. And here's some explanation from another participant, where the person says he or she has to be in a meeting that doesn't really have anything to do with the person. But since the meeting is recurring, the person has to be there, so the person just ended up multitasking. So given all of this, we should really ask ourselves, could the meeting, and especially those recurring meetings, be an email instead? We also find a number of extrinsic meeting characteristics that are associated with multitasking. We find people multitask during meetings to catch up on other work. People multitask during meetings due to some external distractions, such as software notification sound. And people multitask during meetings for anxiety relief. And in terms of what do people do when multitasking, some of them are work-related, such as email multitasking and file multitasking, which also verifies why we choose this particular data for the telemetry data analysis. And of course, there are also non-work-related things, such as browsing social media or doing household chores. And finally, in terms of the consequences of multitasking, there are both positive and negative sides. Well, prior literature talked about the negative consequences of multitasking behavior a lot, such as loss of attention, engagement, fatigue, and a sense of disrespect, which we also hear from people here. What is interesting here is that we also hear from people that they're actually finding some positive experience with multitasking, where people have been talking about how multitasking helps boost productivity. So taking all of this together, this particular work, we provide large-scale empirical evidence on multitasking behavior and task switching over multiple computing platforms. And through our findings, we could come up with a number of best practice guidelines for how to run effective remote meetings. For example, from our study, it might be advisable to avoid important meetings in the morning, reduce the number of unnecessary meetings, shorten meeting durations, and insert breaks, encourage active contribution, and allow space for positive multitasking so that people may have better remote work experience. And from a more human-computer interaction tool building perspectives, in this particular work, we discuss things such as focus mode during remote meetings so that people could concentrate on the meeting rather than being distracted by software notification sound. And we also discuss features in future apps where people could decide which meetings or which part of the meetings they could attend to. And since the publication of this particular work, I feel very fortunate that this work not only gets some kind of attention in academia, but it also gets taken up in the public space. We have been reported by various news media, including Wired, TED, and Forbes. And practitioners are actually using some insights from our particular work. For example, Slack have the blog post on how to run effective remote work. And I also noticed that some institutes like this one from Berkeley HR departments, they're actually using our particular research results as training materials for people on how to better run remote meetings. And finally, this specific approach of deriving empirical evidence using telemetry data to understand meeting effectiveness, it actually has been built into some sorts of features and Microsoft product. And with that, I'd like to conclude my first work, which I think would be a good representative of my line of work, how we have been deriving novel insights using data sets that haven't been really used for research purposes before, and try to use that to derive empirical evidence to better understand how we work. And the second study I want to present here is on the technical methods part, where we have been using AI and natural language processing try to get a better sense of team collaboration experience. And this particular work is conducted here at Stanford with Michael and a group of really talented undergrad and master students. In this particular work, we are interested in also something that is very familiar to us, which is team collaboration. So in our team collaboration experience, I'm sure many of you have this experience that some team collaboration, it ends up very successful, whereas some other team collaboration, it eventually falls apart, where we do not really want to work together with the same team ever again. So I start to wonder, are there any patterns behind team collaboration? How quickly can we get to know that a particular team is going to end poorly? And that's the goal of this particular work, where we aim to classify and predict team viability. Team viability is also a concept that has been studied in prior work by social scientists, which refers to team capacity for future success. It captures the team's interest in continuing to work together, and it reflects team members' satisfaction towards each other. And prior work has shown low team viability could lead to teams fall apart. I'm definitely not the first person to study this notion of team collaboration. Team collaboration has been a central topic in many social science literatures, from management to sociology. Yet, one limitation I would argue for many of the prior work is that they focus on team performance as a metric of successful collaboration, which definitely makes a lot of sense. Yet there are other sides of the team collaboration, such as team viability. High-performing teams, they could also have low viability. Even if the team, say a product team, gets things done in time, or even deliver the product in a perfect way, there could be conflicts in the team where the team members do not really want to work together with each other. So I would say team viability is another side of the story. Yet we lack enough understanding of the mechanism behind team viability. So this present work, we introduce a mechanisms for classifying high versus low viability teams using only team chat interactions. And here are a number of research questions we seek to address here. First of all, can we differentiate high versus low viability teams by analyzing team chat interactions? Secondly, what behaviors are most strongly associated with high versus low viability teams? And thirdly, how much time must the team interact before we can make accurate classifications of team viability? And to answer those research questions, in this particular work, we collected data sets where we have complete chat history of over 660 newly convened online teams from Amazon Mechanical Turk who are performing on creative, interactive, or cognitive conflict tasks over 10 minutes. And by the end of each task, each team member, they were asked to complete a 14-item viability instrument on a 5-point Likert scale, which is some instrument that has been used by prior social scientists. For example, they are asked to things like whether they agree with the statements, the members of this team could work for a long time together. After they complete this particular survey, we summed each collaborator's 14 viability measures into one single individual score ranging from 14 to 70 and calculated the mean of all of the individual score to determine a team viability score, which has the distribution like this. And so the thing that we are interested in here in this particular work is, can we classify high versus low viability teams? And to operationalize that, we divide all teams into two groups. Either they have high viability or low viability based on their viability score. And we set a cutoff viability score as a varying decision threshold so we can answer different sorts of questions. For example, can we classify the most viable teams? And to operationalize, we make it as tasks as classify the top 10th percentile of teams by mean viability. We also have tasks like classify the top 50th percentile of teams by mean viability, as well as tasks as classify the top 90th percentile of teams by mean viability, which in other words is that, can we classify the least viable teams? So this particular task turned into some kind of binary classification model. And in this particular work, we specifically choose a number of explainable machine learning classifiers so that we can better understand what are some of the behavior traits that are associated with team viability rather than just throwing everything into the black box model. And specifically, we report results from logistic regression here, but we also run penalized logistic regression or lasso regression here to understand the behavior traits that are associated with team viability. So here are the specific interactions features that we have been used in this particular work. Broadly speaking, there are two categories: computationally derived features as well as human-labeled features. In terms of computationally derived features, those are the things that we could automatically derive through algorithms, such as work pattern features like message counts or turn taking, as well as linguistic features, which we can use off-the-shelf NLP toolbox to get things like word traces measured through loop categories or sentiment analysis. On the other side, we have human-labeled features, so as to better speak to the rich literature on team collaboration. And here, for human-labeled features, we have another group of Amazon Mechanical Turk worker who manually read and code the transcripts on some dimensions where prior works has shown to be associated with team collaboration experience, such as social loafing. And using those features, we do the classification task. And here are the other results. First of all, in our study, we find that team viability can be classified with high accuracy. We find that classifying top 50 percentile viable teams yields 0.76 AUC score, and classifying top 10 percentile viable teams yields even a better performance, which is 0.93 AUC. And this is something that is really interesting here. The fact that it is easier to classify the most viable teams suggests that the most viable teams, they may share very similar behavior patterns that have been captured by our specific approach. Whereas teams with lower viability, they may be falling apart for different reasons that haven't been captured by our specific methods that well. And the other thing that I want to highlight here is on the right-hand figure. So there are three curves here. They are blue, green, and orange, and they represent the classification results using different feature sets. And the blue curve represents the classification results using only computation-derived features. Orange curve represents results using human-labeled features, and the green curve represents combining all the features that we have. And the y-axis here represents the performance of the classification. And as you could see here, the blue curve tends to be the highest, which in other words means the computationally derived features, using them only, we can get the best performance in many occasions to classify this notion of team viability, which is interesting in the sense that when we think about downstream application, we could actually using this kind of automatic features that could be derived from algorithms to understand team collaboration, and it can be performing even better than human-labeled features inspired by prior literature. And some other results in this study includes, so we find a number of behavior traits that are associated with high viable team. For example, we find active response and engagement is an indicator of high viability teams. Use of exclusive language such as but, either, except, and addressing each other in second-person pronoun, they are significantly and positively correlated with higher viability. And to understand why that might be the case, here's a particular example from our study where these three people, they have been interacting and they have been using quite some exclusive language such as but, either, and except. And you could perhaps see that they are really trying to address each other and having lots of conditions on the things that they are talking about, showing that they have been actively engaging in that particular collaboration. And finally, back to the very first slides where we have the motivations behind this particular study, we investigate the time period that is needed so as to make accurate prediction of where the team is going. And using our data sets, we find that classification of team viability is feasible after only 70 seconds of initial interaction, which is the first 12% of the data that we have. And it achieves 95% of the accuracy from using the full transcript when differentiating the top 10% of the teams. And we see similar patterns for other viability splits as well, which all indicates that there are perhaps enough viability signals embedded in the interaction of team members, within a short time span in the initial interaction. So to sum this up, in this particular work, we look at this notion of team viability, which is kind of like more on the subjective experience of the team collaboration. And we find team viability is driven by a number of underlying mechanisms that are common across different team setups and task categories and can be largely captured and explained by automatic features that could be derived from algorithms. And we think about downstream applications. This could be an interesting starting point. Perhaps we could have an algorithm to have some kind of early detection of low viability teams, giving some kind of recommendations, nudges, or interventions so as to improve the team experience before the team really falls apart. And of course, I would like to point out here in this particular work, our data is limited to online teams working on 10-minute interaction, which is not that representative. In our follow-up work, we actually have been in collaboration with a number of partners, like software engineering teams in the wild, and to see whether such kind of methods could be applied to more realistic workforces. And finally, for this particular work, we do have a website, and we have a functional algorithm there where you could upload your own chats and test out whether your team is viable or not. Okay, so that wraps up the second study, which is on the technical methods aspects. And finally, I'd like to talk about design and how we can leverage state-of-the-art methods and to use that to rethink how we might be working in the future. And this particular work, I got the fortune to work with, to collaborate with a number of students here at Stanford, and, which I feel super fortunate about. Is on using large language model to provide scientific feedback for research papers. And the key thing that we are interested in here is on scientific feedback. As many of us have experienced, scientific feedback is very important for researchers. It improves research works by melding insights from multiple people, and it also lays the foundation of rigorous research where people use that as to gatekeep to watch whether the quality of the research is good enough or not. And there are multiple channels of scientific feedback, and arguably one of the most important channels is peer review feedback, which we are focused in this particular work. Despite its importance, getting quality scientific feedback is really challenging, and especially given the increasing number of paper submissions that we have in some fields like computer science these days. For example, this graph shows the number of iClear submissions over time. And for those of you who are not that familiar with iClear, it's just one of the most important conferences in computer science on deep learning. So this particular conference, 10 years ago, there are just a few hundred submissions, but in 2023, we see over 6,000 paper abstract submissions. So this field has grown a lot. And this is also the case for many other fields as well. And the direct impact of this increasing number of papers in so many different fields is that we see overloading reviewers, and people have been complaining of the difficulties in securing qualified reviewers on the editor or chair sides, which has been shown both over public discussions over social medias where people have been complaining a lot, and also in research papers as well. On the other side, scientific feedback also have implications for equality of science, where under-resourced researchers, they may have even harder times getting timely and quality feedback, such as people who are junior or people who are non-elite institutes or researchers from resource-limited regions. It might be even harder for them to get quality feedback. So the thing that we are really curious about here is, can large language model, given all its incredible performances in so many different tasks, could it provide useful feedback on research papers? So here's what we did. First, we prototyped this particular tool where people could upload the raw PDF of their papers, and then the tool will parse this PDF to get the contents of the paper. And using a prompt, which we carefully tuned and feed to GPT-4, this particular tool could give back the authors some scientific feedback in a similar format as peer review. And after building and designing this particular tool, the thing that we are very interested in is, does it work? And to operationalize, here we conduct a mixed methods analysis to evaluate whether scientific feedback provided by large language model is helpful or not. And specifically, there are two parts of the study. Study one is a retrospective evaluation, where we compare what has been generated by AI versus what has been generated by human in the past. And for the second study, we have a prospective user study and survey, which we HCI researchers are familiar with, where we send this particular tool to actual researchers from over 110 US institutes focusing on AI and computational biology to assess whether they find this particular tool helpful or not. So I'll mostly talk about the retrospective evaluation and briefly talk about the user study, given the time limitation. So in this retrospective evaluation, we first curated two large-scale data sets. One is from Nature Family journals, covering over 3,000 papers and over 8,700 human written reviews, covering 15 Nature Family journals. And we have another data set from ICLR, the deep learning conference, with over 1,700 papers and over 6,500 human written reviews. And we specifically chose these two data sets to ensure the coverage of these particular data sets. So they have different characteristics. For the Nature Family Journal data sets, it covers a wide array of scientific fields from niche to high impact journals. Yet its limitation is that there's some kind of self-selection process in this data, that it only contains reviews for a number of accepted papers where the authors are willing to share the review process. On the other hand, ICLR data sets, it focuses on one single field on machine learning, yet it contains all the reviews. It contains reviews of both accepted and rejected papers. And the core part of this particular work is a retrospective comment matching pipeline. For both the AI-generated feedback and human-generated feedback, we first use GPT-4 to get a summarization of the key common points for that particular work. And after we get a summarized key point of those points from AI or human-generated feedback, we then ask GPT-4 to evaluate to what extent they are similar to each other. And based on the similarity score, we calculate a coefficient of the matching to represent to what extent they overlap with each other. And this particular pipeline we validate using human verification, which proves to be pretty good performance. And here are the results we get from this retrospective evaluation. First of all, we find large language model feedback significantly overlaps with human-generated feedback. Around 30% of the comments raised by GPT-4, it overlaps with comments from one individual human reviewer. And to put that into context, the overlap between one human reviewer and another human reviewer for the same paper is also around 30%. In other words, GPT-4 at a high level is giving some feedbacks like another human reviewer. We find similar patterns over the ICLR datasets, and such trends hold for different subfields. And we also find something really interesting here, that the overlap between GPT-4 and human reviewers is larger for weaker papers. Where we stratify the results by ICLR decision outcome, we find for rejected papers, there are actually more overlaps between AI and human, which is interesting in the sense that those weaker or rejected papers, they might also be the papers that need most feedback from people. So I just showed some kind of results on the overlaps between AI and human. You might be wondering something else. Even though that there's quite some kind of overlap between AI and human, its large language model only generate generic feedback that could be applied into all the papers. Say, the large language model could be generating things like this paper lacks novelty and it can apply to many different papers. Is that the case? And to operationalize that, in this particular work, we conduct a random shuffling exercise where we have the null model, large language model, mostly produce generic feedback that applies to many papers. If that's the case, if we shuffle and randomly match the review and the paper, then we should expect to see no change in overlap if the feedback is generic that applies to different papers. However, after the shuffling, we see significant decrease in overlap, indicating that the large language model feedback is paper-specific. And here are some other results that I want to highlight here. The comments raised by multiple human reviewers, they are more likely to be hit by a large language model. Arguably, those are the points that people have consensus on and are more central to that feedback process. And finally, we see GPT-4 tends to focus on certain aspects of scientific feedback, such as implications of the research, whereas people, on the other hand, focus a lot on things like novelty, adaptation experiments, and missing citations. Okay, so that's the retrospective evaluation. And we have another prospective user study to further strengthen the results. And we send out this particular tool to researchers from different institutes to see whether this tool could be helpful for their particular work. And here are some of the key findings from the user study parts. We find researchers say large language model feedback to be helpful. More than half of the users found GPT-4 generated feedback helpful or very helpful, and over 80% of them found it more beneficial than feedback from at least some human reviewers. And we also hear from people the large language model feedback indeed overlap with human feedback. Over 70% of participants think there is at least partial alignment between large language model feedback and what they think or what they would expect to get on the significant points and issues with their papers. And we have many other results on the surveys which you could check out in our paper. So given all of this together, in this particular work, we use the design and we prototype and build this particular tool, and we evaluate in a systematic way whether such kind of large language model could be helpful for the scientific feedback process. And I would like to emphasize here, while human expert feedback should always and continue to be the foundation of rigorous scientific process, this particular tool could be helpful in some ways, and especially when timely expert feedbacks are not available, and for example, in early stages of manuscript preparations before peer review. And this is an ongoing effort, and we have been also thinking about whether we could do some kind of random experiments to test out the effects of AI feedbacks in a while. And finally, this particular work, even itself hasn't really gone through the peer review process. It gets some kind of attention, and people have been discussing the relationship between AI and peer review. Okay, so that wraps up the three main projects that I would like to talk about today. And for the final few minutes, I would like to briefly talk about some ongoing and future work. And again, back to this diagram, I have been really fascinated by this notion from Simon to establish empirical evidence, technical methods, and design to better understand computing technologies. And on my side, really interested in how technologies is helping work. And here are some specific problems that we have been exploring recently and thinking about doing that in the future. And I think AI has lots of implications for the future of work. So many of my work speak to generative AI. First of all, I'm interested in quantifying the effect of AI usage and how AI could be influencing and getting some kind of downstream impacts on how people work. For example, how do people use generative AI tools in their work? In what particular scenarios? And what can be its impacts on the workforce? As a representative of this line of work, I've been involved in a number of really interesting projects where we have been looking at ChatGPT usage in academic writing and to understand how people have been using ChatGPT in academic work. And one particular study here, we find between 6.5% and 16.9% of texts submitted as peer reviews to top conferences in CS could have been substantially modified by large language model. And that could really raise some kind of discussions on how we should be thinking about AI feedback and AI work. On the technical side and on the design side, I'm interested in continuing my work to build and evaluate workplace applications, especially in a wild fashion. So many HCI works, we look at with prototypes and we do user studying in the lab. However, it could be different from how actually people use that. So I've been involved in a number of ongoing works with few partners on designing and evaluating AI-based team communication intervention tool, which is based upon the idea of the second project that I talked about on team viability. And specifically, we have been trying to incorporate different activities, including the team interaction over language, as well as things like GitHub activities, since this is a group of software engineers, and using other informations, try to predict some sorts of team outcomes, such as satisfaction or performance. And in the future, we're interested in exploring interventions to help this group of team work better. And finally, in terms of design, I'm interested in something that is about human generative AI interaction guidelines, which I think could be some kind of foundation for many of the product design in the future. So the thing that I've been curious about is, in which context AI provided the greatest utility? How should it be presented to the end user? Would it be just a ChatGPT type of interface, or probably not? And what would be the level of control versus agency, privacy versus performance trade-off that is most preferred by human? Or in other words, for different types of work tasks, how can we map out its considerations and build tools that people are willing to use? So we have some kind of initial results working together with a number of few practitioners where we have been surveying for different types of tasks. What do software engineers and what do the general public and what do the researchers think about those dimensions to building a tool that people are willing to use? And of course, this is the initial step, and I would like to broaden that in the future using experiments and prototypes and to test that in the wild. And with that, I would like to conclude the main part of the talk. And for the final few minutes, I would really like to conclude by doing some kind of acknowledgements, since so many people have helped me so much during this PhD process. So to begin with, I would like to thank my advisor, Professor Dan McFarland. Dan has always been an invaluable source of ideas and motivation for me. As someone coming from an engineering and computer science background, I'm really fascinated by Dan's lots of sociologist type of imagination. It really broadens my view and helped me a lot. And also, Dan has been super, super supportive of me during the process. And as he mentioned in the very beginning, I have faced lots of rejections and failures during the course of PhD. And Dan always says, keep trying. And hopefully I made some parts of that, although I still keep failing. And I would also like to thank Professor Michael Bernstein, who is my CS co-advisor. And Michael there are so many things to talk about Michael, and it is Michael who introduced me to the field of human-computer interaction and social computing during my rotation project. And also it's then I got involved in projects working together with people from business school and from management science and engineering. They really helped me to rethink what's my core interest. And other than that, Michael has taught me so much in research, collaboration, and teaching, which I really feel gratitude about. And I would also like to thank my committee members here, Professor Dan Jurowski, Professor James Stowe, and Professor Dee Yang. So I get to know these wonderful people and getting to know different aspects, how to bridge computation and social science together, which make me even more convinced that I will do something related to computation social science in the future. And many of the conversations with them on the careers and on research really helped me become a better and more mature researcher. So I'm really thankful for them. And then there's this screen of other amazing advisors, mentors, and collaborators that I have during the course of my PhD, which I try hard to fit them in a single page. But I got the fortune during my course of Stanford, during my PhD, to work together with people at Stanford, at Microsoft, at Allen Institute for Artificial Intelligence, as well as other institutes, which has been listed here. And I feel very fortunate to be working together with them and to get the work done, which I feel really, really appreciated. And other than that, on the professional side, I would also like to thank my fellowship to make my graduate school possible. So I got funded by Stanford School of Engineering Fellowship in my first year, and also for the last 3 years of my PhD, I got the luck to get the Stanford Interdisciplinary Graduate Fellowship, which makes all my work here presented today possible. Okay, and then going on to the personal note, I'm really thankful to my friends in Stanford HCI group, Stanford Mimir Lab, as well as computational sociology workshop, as well as many friends that I get to know at conferences. And I feel very fortunate to have these groups of friends to support me over this process. And and there are other group of friends who we play music together. And of course, I would like to thank my parents, and I feel really fortunate to have such nice parents to be encouraging and giving lifelong motivations. And through a young age, they have been telling me that you should pursue something that you're really excited about. And here I am, and now I'm find something that I'm truly excited about. So I'm really appreciative of that. And of course, I would like to thank my partner, Mingxing. And I got to know Mingxing during the pandemic, and she has been so supportive of my work unconditionally. And I feel really, really appreciative of having a partner. And we are actually going to have our wedding very soon at Stanford Memorial Church. And I'm looking forward to the path forward. And last but not least, I should thank this guy as well. He is Pino, the corgi of Pat, and he just celebrated his first birthday. And I got the luck to have him, and it feels just so joyful and comforting to be with him, and especially when I was navigating through the job market earlier this year. So yeah, with that, I would really like to thank everyone for showing up here and conclude my talk here. Thanks everyone, and I look forward to your questions and comments.
We have a couple minutes for questions from the audience, and then we will go into the closed session where the snake is waiting.
Yeah, thanks for the great talk in defense. I'm really curious to hear your thoughts on this discrepancy that you hinted at in your talk, which is the stigmatization around AI-generated feedback, such as in the application of peer review. Mm-hmm. But then also in, I think, study 1 or study 2, you had highlighted that there was a lot of positive perception of the AI-generated feedback. And so I'm kind of curious if you could talk a little bit about that discrepancy and how you might expect that to lead to behavioral changes in the future for future interventions that you alluded to too.
Yeah, that's a great point. So I guess there are multiple aspects that I could have in response to your questions. So first of all, this is the discrepancies that we have with regard to AI and human on this particular model, GPT-4, and also it's generated from that particular prompt that we used in this particular case. So I would say at a higher level, it is still unclear for other types of model or for other types of prompt. Would there be still similar types of discrepancy as we've described here? And other than that, I would say it's most likely there's going to be some sorts of discrepancy. And I would say we hear this from people a lot, which is interesting as well, where people have been pointing out that large language model can actually generate something that is novel that people have not been mentioning, which I think could be some useful and interesting angles for the future. So I'll be thinking about in the future, when we talk about human and AI, definitely human is still going to provide feedback for the other people, which is really, really important. But on the other side, potentially, we could also be hearing from AI, for example, getting the first pass of the review to get some idea of how other people might be thinking about this particular work or just to improve that particular paper. So that will be helpful. And of course, I think there could be some kind of interesting application in the future where combining the insights from both human and AI and try to get a more collective intelligence, this kind of hybrid human AI intelligence, so as to get better innovation outcome. But yeah, I think this is still really in the early process, so we cannot say for sure what's the exact discrepancy. But I think this is an interesting angle, and we should definitely explore further.
Yeah, really great talk. My question is actually related to this previous one and specifically related to your third study. So I wonder, are there variation in terms of the perception of toughness helpfulness in using this kind of large language model for generating scientific feedback among different populations. For example, among undergrad students and the professors, are there this kind of variance in terms of perceptions?
Yeah, thanks so much for this question. And to be honest, I actually just cut this particular slide due to the limitation of time. But yes, yeah, we indeed have conducted some kind of analysis like this, and we find that this level of perception of helpfulness is kind of consistent across different groups, whether it is, say, a junior undergrad students, or is it postdocs, or like established researchers. They find some sorts of merit in using such kind of tool, which I think is really interesting. It's suggesting that AI could be helping a different range of audience rather than one single group. Yeah.
I have a final question, please.
I have a question about your Likert scale with the 14 different points for studying team productivity, or team viability.
Yeah.
As someone who's filled out these surveys before, now I know that sometimes you just add all the different numbers up and then you have one composite score. But I'm wondering if you did any analysis on the individual components of that, and in particular on how teams, they're kind of different things, right? And some of them might speak to different team dynamics, like you do a qualitative even analysis of that.
Right. Yeah, that's a great point. We didn't look specifically into individual response for the sake of this particular project, but I definitely have taken a look at it, not published in anywhere. But I think there are many different interesting things and different patterns of collaboration that is interesting going on. So for example, one extreme would be like everyone on the team, they feel like the team is great, and like the team is in good viable status. And there are other extreme where people, they feel they don't want to work together with each other, and everyone have low score. But there's also something interesting in the middle where like some people, they feel they have a good time working together with the others, but others on the team, they perhaps have some other ideas. They think like they do not want to work together with the same group. So it's kind of like directional in some sense. So yeah, I would say like it would be interesting to look at how this kind of different patterns or different modes of collaboration, and to think about how people perceive the other team members on the team, and how does it influence some of the outcomes. So the outcomes that we show here is at the aggregated team level, which is important, but I think it's also important to consider the individual subjective feelings, since by the end of the day, when we think about individual worker, it is their experience that would influence things like whether they want to leave the organization or they want to continue working together with the group. So yeah, I would say like another model that is looking at how the environment or how this kind of process can be predictive of individual outcomes. It could be very interesting as well. Yeah.
All right.
Okay.
Congratulations.